All right, so hopefully you've gotten quite a ways in. I've started to write my work up here. We'll talk through the first couple lines here. The idea is the first step of variation of parameters, we got to solve the homogeneous equation first, right? Before we solve the inhomogeneous one, we got to start by finding our complementary solution, the solution of the homogeneous problem. So to do that, I generated my auxiliary equation, and then I factored it, I found my roots, and I formed my solution, the homogeneous problem right here. Any questions about that solution to the associated homogeneous problem? Okay. So the idea is when we take this, the big idea is that we make an assumption now. We guess the form of our particular solution to look like some function times x1 plus some function times x2. That's really the big idea. And what happens is we take that guy in that form, we take the derivatives, we plug it into the differential equation, simplify everything, and we're left with a system of equations, that have a k1 prime and a k2 prime. And we can use Cramer's rule then to solve for the k1 prime and the k2 prime. And in the end, we can kind of simplify the notation of that process by thinking about it in terms of these two Wronskians here. That should be W here, not W2. Sorry about that. So because I'm going to end up using all that stuff, I'm just going to mechanically calculate these three values separate. I'm going to calculate W, W1, W2, because then I can use them to find my K1 and K2. So W is the big one. That's the Wronskian. That's the one that's known by mathematicians, right? In different areas as well. So we calculate that guy. I took the derivatives, took the determinant, 8 times e to the 4t. Any questions about that line? That's what we got for the Wronskian. All right, then I went on W1. W1, not some fancy mathematical notation, right? It's just W. It's the Wronskian, except we're changing the first column, so let's call this thing W1, right? It's just some little trick to help us remember. So all I do is take that Wronskian guy, and I replace that first column with 0, and then the function, f of t. Same thing, calculate the determinants. Now we got negative 2 e to the 7t. We'll do the same thing for W2. Now you take the Wronskian, instead of replacing the first column, you replace the second column with 0 and f of t. Any questions about the calculations of these determinants? All right. Now we move on to actually calculating k. Well, k1 prime is equal to the ratio of the determinants, that guy. So k1 is just the integral of that ratio of determinants. So I'm integrating the ratio of the determinants in here, simplifying, integrating. I have that value for k1. Now I'm going to move on to k2. K2 is just going to be the integral of W2 over W1. So that's going to be the integral of 2e to the negative t divided by 8e to the 4t. So I got 1/4 e to the negative 5t when I simplify that. Pull out my constant. When I integrate the exponential, I get e to the 5t plus that extra factor of negative 1/5. Looks like I have negative 1/20th e to the negative 5t. That should be my k2 value. All right, then my assumption was that the particular solution was k1 x1 plus k2 x2. The whole idea was I just had to find out what these k's were. Now I got them. Now I can form the particular solution. It is k1 negative 1/12 e to the 3t times x1. x1 was e to the negative 2t plus k2, so negative 1/20th e to the negative 5t times x2, which in this case was e to the 6t. Now, somebody asked me in an earlier class, we have to simplify that. And in the past, I've gone back and forth, but I'm going to say, yes, you have to simplify this. Right? Why? Because this looks really ugly. I can't see what's going on. I don't know what's happening as t changes. That big, long expression means nothing to me. But when we simplify it, we're really going to get a much cleaner form that actually tells us what's going on with the problem. So I can simplify the first piece to negative 1/12 e to the t. Then I have minus 1/20th, once again e to the t. So I got e to the t times, how about negative 5/60 minus 3/60. So negative 8/60 or negative 2/15. That's just a nice clean version of this xt value. Now I can see what happens as t changes. This piece is going to get bigger and bigger in magnitude, right? Must be subtracting more and more exponentially. If that was a negative up in that exponent, I'd have a transient term. And as time moves on, it would become less effective on the system. And this extra piece here is really going to be related to an important part of our system. For modeling some sort of motion, oftentimes this is the piece associated with the external force. So you got a motor system. This is the part that's going to talk about the motor effects. Okay? So it is important to get this nice simplified form. Is that my solution? No, my solution is xc plus xp. Complementary solution plus the particular solution. So I have c1 e to the negative 2t, c2 e to the 6t minus 2/15 e to the t. And that is the solution. All right. Questions about the process? Any questions? All right, there are a lot of questions in the homework. Most of it is just mistakes along the way or challenging integrals. This is the kind of integration I would expect you to be able to do on the exam. So these are ones you would do by hand. The ones on homework, not so much. And some of those are a little bit ugly. So feel free to use your calculator or Mathematica to do those integrals along the way. That's totally fine. Okay, but if you're running something like this on the exam, I expect you to be able to integrate it and get to that nice clean solution. Okay? All right. All right, so that's certainly a process, right? Kind of long. This is the one that you're supposed to do this at home over spring break with your parents, because then they think you're learning a lot here, and we'll give you, money to come back with, right? But do we have to go through this long process? Not necessarily, right? We do have another technique. This is the same problem here. Can we apply indeterminate coefficients? This is the process we talked about last time. And the first question is really, can we apply this technique to this problem? What are we checking for? One, we're checking for the coefficients on the left-hand side. We can only use this technique if those are constant coefficients. They are. Pretty much always will be in this class, because those are the only way we know how to find the complementary solution. So that's pretty much what we got to work with. But we do have a restriction on the right-hand side. This has to be kind of a, quote-unquote, nice function for us to be able to use this technique. Is this a polynomials and sines or cosines, or any sum product of those pieces. Okay? So I couldn't do it if it was 1 over t, or the natural log of t, or arctangent of t. But for 2e to the t, totally fine, we can use this technique. Okay? So we got to check and make sure we can use it. We got to find our complementary solution. We did that last time. It's c1 e to the negative 2t, c2 e to the 6t. And the whole idea here is we're going to assume the form of f of t. We're going to assume the form of xp, and we're going to say that it looks like f of t. So f of t looks like some number times e to the t. I'm going to guess that xp looks like some number e to the t. That's my guess. Now I make this guess. How do I find a? All right, so this is one of those big ideas. This is the theme, right? So we do something. We get some sort of parameters. We need to take the derivatives and plug it in. Right? This is a big idea. Over and over again. So I want you to say that out loud, right? So you're going to say, take the derivatives and plug it in. Everybody else together. Take the derivatives, plug it in. One more time. Take the derivatives, plug it in. All right? We've seen it a whole bunch of times, right? We think it's assumption. Hey, 1x, 1k, 2. But then how we do this, we take the derivative, plug in, and find the parameters. These are kind of a small version of variation parameters. In the first figure, same idea. We make an assumption that has parameters. We take the derivative, plug it in, and figure out what the parameters have to be. Big thing. Yeah. Right, right. Basically, that linear independence idea. Like, not multiples of each other. This is really a different guy. Absolutely. Good question. All right, so I have my guess here. So I got to find this. So I'm going to take the derivatives. I'm going to plug it in. Xp prime is, well, ae to the t. Xp double prime is ae to the t. Go ahead and plug that into the differential equation and see if you can solve it for a. Plug them in. Looks like I got a negative 15 of these guys over here. Maybe divide through by e to the t, divide through by negative 15, negative 2 15ths. Looks like xp is negative 2 15ths e to the t. So that means my solution must be c1 e to the negative 2t, c2 e to the 6t, minus 2 15ths e to the t. How's that? This is a quick technique. It can be really easy and not easy on the right-hand side. So we have some nice clean right-hand side, e to the t, sine of t, t plus 1, some nice little polynomial. This is a nice quick down and dirty approach. Okay? You just make your assumption and figure out the constants, boom, you got it. Okay? Any questions? All right, of course, it's not really that easy. There's some other things to consider, so that's what we're going to look at next here. All right, plan of attack. Okay. Before we hit number one, I'm sure what you're all really waiting for, and my graphics are doing right. I picked Wisconsin as Villanova upset. Thank you very much. Right? I picked Michigan over Louisville. I picked Duke to win the whole thing. So I'm pretty much done. All right. But what are we talking about? Finish undetermined coefficient. So choosing the form of xp, I just kind of said, well, some number e to the t. That's good in some cases, but sometimes it's more complicated, right? So how do we kind of generally choose that form? After that, adjusting for the overlap, right? Somebody already asked about it. What happens when we have an overlap with our complementary solution? We'll talk about that. We'll do a practice problem. A couple other notes here. Skip 2.7. It's on the schedule, but actually in one of the revisions of the text, the section numbering changed a little bit. So 2.7 is about all the stuff we kind of talked about from a linear algebra, deep linear algebra perspective. Really interesting stuff, really important. I encourage you to read it on your own, spend a weekend, good stuff. But we're going to move past it and get a 2.8 on some applications. So that's what we're going to spend time on. The purpose of the applications is also going to be to set up problems we can practice our techniques on. That's really what we're going to focus on. So we're going to start that on Thursday. We're also going to have a quiz on Thursday. Following Tuesday, we'll have a big review day in class. And the following Thursday will be exam 2. That will be in class like the last one. Yep. No, this is really going to focus on chapter 2. It's going to focus on higher order differential equations. I would love to make it cumulative. I just don't have the time. So, unless you all want to hang out for another hour. 2-hour exam? Anybody? No? Okay. Just chapter 2 then. Yep. Yes, everything should be returned. Pretty much everything is graded. Scores should be entered as of last night, maybe late. I didn't really get them back till this morning. So We should return both quizzes on Thursday. Practice exams will go out on Thursday or Friday as well. I have caught up on posting my notes. Sorry about that. I checked the page, like 1.2 is posted. Sorry. And I have updated the videos as well. All right. Other questions? All right. Let's finish up undetermined coefficients. All right. Choosing XP. How do we choose XP? All right. Well, here's the new problem. X double prime minus 2x prime plus x equals t squared. Right? A natural point here, a natural starting point might be, hey, let's choose XP to be some number times t squared. That's pretty much what we did last time, right? We'll try it. See what happens. Take that guess. See if you can figure out what that undetermined coefficient is. Well, you know what? Actually, yep, no, that's fine. That was the wrong part. That's good. All right, before I get too far here, let me just calculate some pieces here. XP prime is 2a to the t. XP double prime is 2a. And right away, I kind of have a problem, right? And here's my problem. I'm looking at that problem and I'm saying, okay, these derivatives are giving out values of t and then some constant value. But because the left-hand side only has constant coefficients, it's basically saying we need to add or subtract multiples of these guys to get to t squared, right? But I have a t there. Like, how am I going to get rid of the t? I can't take some linear combination of t squared and t and get rid of the t. So the only reason to get rid of the t value and the constant value is if a is equal to 0. But a can't be equal to 0 because then I have x equals 0, right? So the problem here is that I need some extra ways to manipulate these other pieces so I can get rid of that t value. So I can get rid of the constant value. Somehow take the linear combination of these derivatives and somehow just get the t squared piece. Okay? So what do I have to do? Well, I can't just get this because I don't have any kind of degrees of freedoms, any levers I can pull to get rid of the t term. So what I have to do is I have to add some constant times t, right? Because if I do that, I'm adding an extra lever that I can turn or pull, right? Now I can adjust the value of b, and maybe that will help offset whatever I'm doing at a to eliminate that t term. So when I took the next derivative, I realized I have a constant term. And now I need something to get rid of that piece. So I have to do the same thing. Well, let me add a constant term to my general guess here. Okay. And so now I have kind of the flexibility to adjust each one of these individual pieces to find the right combination that gives me the right value of the coefficient of t squared that I want, but also eliminates the other two pieces. Okay? So I do adjust my guess to be this. Now, when I do that, xp prime then becomes plus b, and xp double prime is still just 2a. So I have these values. And there's a couple ways you can think about this. One, you could say, well, the right-hand side, that's t squared. Actually, what that is generally is a second-degree polynomial. And so what you needed to use for your guess was a general second-degree polynomial. So that's what I have here, at squared plus at plus c. So the way I want you to think about it is, what I need is I need to be able to take the derivatives of my guess. And I need to have a factor or a term for each one of the different pieces I get. If I take the derivative and I get something new, I have to add that new thing to my guess. All right, we're going to build on that a little bit here. Let's just finish this one up here. So that is my guess, xp. And now I've taken the derivative and the second derivative. I'm going to plug it in now to find out what a, b, and c are. So I plug in x double prime to get 2a minus 2 times x prime plus x. That's supposed to equal t squared. I need to find the right a, b, and c to make that thing equal to t squared. So how do I solve this? I just take the left-hand side and group it as a polynomial. So I'm going to look for t squared terms. This is my only t squared terms. So I have a t squared. Then I'll look for t terms. There's a t term, and there's a t term. So it looks like I have minus 4at and plus bt. And I have my constant terms. Here's a constant term, and here's a constant term, and here's a constant term. So I have 2a minus 2b, because I distribute that minus 2, and plus c. Those are all my constants. And that is apparently equal to t squared. And so now I have a polynomial on the left, I have a polynomial on the right. The only way they're equal is if their coefficients match. So I say, what is the coefficient of the t squared term over here? 1. So a must be equal to 1. Nice, clean equation, right? They don't always come out that clean, but that one's certainly nice. Now, if I take this little piece right here and maybe rewrite it by factoring out that t, it would be minus 4a plus b. What's the coefficient to the t term on the right-hand side? 0. So that means minus 4a plus b must be equal to 0. So you see how the b, by having that b in my guess, it allows me to pick the right value to eliminate the t term, right? A is kind of fixed. A has to be whatever is going to get me to t squared. But now I have added this b piece, lets me eliminate the t term. And then over here, my constant on the right-hand side is 0. And on the left-hand side, I have all that stuff. And so once b is fixed, that c is now going to allow me to get rid of the constant term. So I'll have 3 equations, I'll have 3 unknowns. In general, I could use linear algebra to solve this. In this case, it came up pretty cleanly, so I really don't need to. I know a is 1, so that means b has to be 4. Plug those guys into the last one, I'll have 2 minus 8 plus c equals 0. Looks like c must equal 6. And so I now know that my particular solution is going to be t squared plus 4t plus 6. And then, of course, for my general solution, I take my complementary solution plus this piece. All right. Questions? Okay, the big idea here is that how did I choose my XP? I looked at the right-hand side, and I'm basically going to take all the derivatives I'm going to need for the equation. I have to look to see all the different terms I get by taking those derivatives. And I need a term in my guess for each one of those unique terms. Okay? So let's look at another quick example here. Let's say my right-hand side here was instead, so instead of x double prime minus prime plus x equals sine of t. Okay? Sine of t. Well, once again, I'm adding combinations of its derivatives. What's the derivative of sine? Cosine. Second derivative gets me back to sine. I don't really care if there's a negative sign. Well, basically, when I take the derivatives, I either have sine terms or I have cosine terms. Okay? So that means for my guess here, at the form of my particular solution, I have to have a constant times sine plus a constant times cosine. Because if I don't All right. So our method for guessing is to take the derivatives of f of t and use all the forms that are present. So if I'm considering a second order differential equation where this is the right-hand side, I'm going to start taking derivatives. The derivative of this guy is going to be derivative of the first times the second plus the first times the derivative of the second. Second derivative. Well, I just did that one. So that's going to be this whole thing. And now I need to take the derivative of this guy, derivative of first times the second plus the first times the derivative of the second, something like that. Now, I'm not simplifying this. I'm not canceling out and doing some other crazy stuff. I'm just looking at all the stuff I got. What do I have? It looks like I have some number times e to the t cosine of t, right? I got one of those right here. What else do I got? Well, I got one of these guys. I have some number times e to the t sine of t, right? I don't need the negative. I have a constant up front. Do I have anything else? Not really, right? Constant e to t cosine t, same thing here, same thing here. That's it. So that would be my guess. See if you can apply that same idea to the next one. What if that was your right hand side? What would your guess All right. Definitely need one of these guys, right? I mean, I see that to start off with. Then I take the derivative. I get the derivative of the first thing times the second plus the first thing times the derivative of the second. Looks like I got a new guy over here. So I'm going to have to add something that looks like that. Okay? What about this guy? He's already accounted for. Now I take another derivative. Now here I have the derivative of the first thing times the second plus the first thing derivative of the second. Over here, first thing derivative of the second derivative of the first thing times the second. What about this guy? Is he new? This one? Is this guy new? No, I already got one of him. What about that guy? This guy? Yep. So I have to add a constant e to the t. That would be my guess. Now I can factor out that e to the t and write that as a t squared plus bt plus c. And you can certainly think of that. Here I have basically a second degree polynomial times an exponential. So there's my general second degree polynomial. I don't really need a constant in front of the exponential because, well, I could just distribute it. And I have a bunch of new constants anyway, right? So you can kind of get a pattern for these based on their types. I really encourage you to think that. Any questions about forming our guess here? Yep. All right, if we had a third order differential equation, I mean, you really want to see all the different pieces that are going to be in there. But when we're talking about polynomials, exponential functions, and trig functions, right? So trig functions, sines and cosines, not even, they go back and forth. So you're only going to get sines and cosines. So you won't take 10 derivatives if you know that's going back and forth. Exponentials are always exponentials, right? And if you have a 10th degree polynomial, you know what you're going to get with all those 10 derivatives. So you really don't have to take them either once you kind of recognize what's going on. Good question. All right. All right. Try this one, right? I see some smiles. They're like, that looks too easy. I mean, it looks like a constant, right? So I guess A is my particular solution. That seems reasonable. I take the derivative, I get 0. Take the second derivative, I get 0. I plug it in, I get 0 plus 0 equals 4. That's the problem, right? All right, so what's going on here? Here's what's going on. I start off by finding my complementary solution. Okay? To do that, I generate my auxiliary equation, r squared plus r equals 0. This factors into r times r plus 1 equals 0. That gives me roots r equals 0 and negative 1. So my complementary solution is c1 e to the 0 t plus c2 e to the negative t. So am I surprised that my guess of a constant returned as 0 for the left-hand side? Well, no, because it's one of my complementary solutions. Right? If I take a complementary solution and I plug it into the left-hand side of the differential equation, it's going to give me 0 every time. Okay? So I guess A, the problem is there's an overlap with my complementary solution. It means basically contributing no information to me. No information to help me figure out how to get to 4. Right? So what do? When I have this overlap, I have to adjust my guess. Here's the magic. You multiply by t. Okay? So I checked my guess. My guess was some constant. I recognize there's overlap. I say that's a bad guess. And I modify my guess to my previous guess times t. That's it. And now I take the derivative. And I take the second derivative. And I plug that in and I get 0 plus a equals 4. So a is 4. That tells me my general solution is c1 c2 e to the negative t plus 4t. Questions? Any questions? Yep. If it was x prime plus x plus x, would that have a equals 4? Well, if I had that extra one, so then I had r squared plus r plus 1, right? And so I don't think that r equals 0 would be one of my roots. And that's what's giving my constant. So it really just depends. I mean, you just do that process like you're solving a homogeneous problem, right? And your complementary solution is whatever it is. And the only issue is if it overlaps with our guess. Right? If it doesn't overlap, then you're in business, leave it to be A and you'll be all set. Okay. What if I had a solution? What if my root was 0, 0? And then my solution would look like constant plus constant times t. Then what would I have to do? Multiply by t again. Right? I would just keep multiplying my guess by t until there's no overlap. All right. How come I don't have to add this b? Haven't I talked about using the general first degree polynomial a bunch of times? I could actually add that b. But what's going to happen is when I plug that in, that's basically a complementary solution. So you'll find out that b is equal to 0. Right? So you don't want to add it because it just makes your computations harder. Okay? So in this case, we just adjust our guess by multiplying through by t. All right, there's kind of the statement. So when your guess must not match term from the complementary solution, you modify your guess by multiplying through t. And when I say t, what do I really mean? Independent variable. Yep, absolutely. By the independent variable. All right. Okay. All right. There is the differential equation. X double prime minus 2x prime equals f of t. And the idea is if this is f of t, if f of t is 2t, what would your guess be? What would your guess be? What are you going to use for xp? What do we have for xp here? The majority of people say A. Fortunately, the majority of people also thought they picked good brackets. A is not correct. B. There we go. Why B? Why B? Well, let's look at our differential equation. The first thing we have to do is find that complementary solution. My auxiliary equation is r squared minus 2r equals 0. That factors into r times r minus 2 equals 0. So r is equal to 0 and 2. My complementary solution is c1 e to the 0t plus c2 e to the 2t. So I do make that initial guess of AT plus B, but there's overlap between my complementary solution. What do I have to do? I have to multiply it by T to get that for my guess for XP. Okay? So it's because there was overlap with my complementary solution. Yep. What's that? You will, that's true. So it's one that will work, but it's much harder, right? The idea is that, this is a nice case where it's 2t, right? But on the other hand, this could be like 2t times sine of t, in which case you're still going to use the core form of this polynomial, but it's also going to be multiplied by sines or cosines or potentially exponentials. So adding that extra c that's going to mean nothing could really increase your computation. Like here, it's not a big deal. You can kind of handle the same, right? But in a harder problem, that c could really cost you a lot of time. Right? So, right, we're going legally. You want to say, well, technically this was also good work. Right? I should teach you, right? I will work. But the best guess is B. You don't want to add that constant. Okay? Good point. Yep. Other questions? All right. What about the next one? What about this guy right here? Let me stop this one, start a new one. All right, mostly E's, a couple D's though. All right, how do we tell? Well, I'm thinking of the derivatives. You know, if I take some derivatives of this, I would take derivative of the first times the second would give me something like this, plus the first time the derivative of the second would give me something like this. If I take more derivatives, I can kind of see I'm going to get these things over and over again. All right, so really, I can see that I'm going to need a constant e to the t, and I'm going to need some constant t e to the 2t. That might be a good first guess here. So I can factor that out if I want to get bt plus a, something like this. But I got to check for overlap. Is there overlap with my complementary solution? There is. I have constant e to the 2t, and I have constant e to the 2t here. So what do? I multiply through by t. So my better guess is, my guess I need here is bt squared plus at. Okay? If you switch your b's and a's, it's wrong. No, I'm just kidding. Right? Doesn't matter. A's and b's, right? They're just constant names. The book's going to use c's and maybe some d's in there, right? So it's all good. Any questions there? All right, so the book's also going to talk about another approach called the annihilator method. The annihilator method is just another method to generate the guess for xp, to generate your general solution form here. You still, once you get that, have to go through the process of solving for the coefficients, okay? And I'll kind of talk through kind of briefly what that looks like. It basically says that if you have something like this, you have this differential equation, one thing you can do is I could just multiply, I could just take the derivative of the whole equation. If I take the derivative of this whole equation, what do I get? Well, I get x triple prime plus x double prime equals 0. And that way I've kind of turned this into a homogeneous equation. Right, well, that's great. If I'm working with the homogeneous equation, now I can think about roots and what to do here. So I could generate an auxiliary equation that looks like r cubed plus r squared equals 0. It has roots of r squared, r plus 1 equals 0. It has r equals 0, 0, and 1. And if I form the solution to this homogeneous equation, it would look like some constant plus some constant times t plus some constant e to the t, or negative t. That should be negative 1. Okay? And the idea is in my regular complementary solution, I had this piece and I had this piece, which means this thing should be my xp, my 4. So eliminate the thing on the right in terms of homogeneous problem, and then when you solve that using your homogeneous technique, the pieces that are not represented in the complementary solution become the appropriate guess for your xp. Okay? So it is a good approach in terms of kind of skim through that section. I'll get kind of an overview here of the number. The reason I don't stress it too much is because this one's not too bad. How do you read the form? But if there's a sine or a cosine over there, it's a little trickier. It's a little complicated, right? And so depending on how complicated the right-hand side, you almost have to kind of memorize these weird forms of d's and combinations used to eliminate it. I kind of prefer just the unknown coefficients, where I can take the derivatives and grab forms in general. So that's why I don't focus on it, but it's a good read. The last thing I will leave you with is my practice problem here. I would encourage you to write this one down. Give it a try. We'll start class with it next time. I won't give you a ton of time in the class to go through it, so if you can sketch out how you're going to do it or get through it, and then I'll go through it in detail, that'll be a good start to class, right? I know you're debating, like, should I do this problem? Should I read that extra section 2.7 on linear algebra? I'm not sure which one sounds better, so I'll let you pick, okay? All right, that's all I got.